Recording started.
Okay, here we go. So this is going to be the review for this unit on forces and structures. And again, also that assignment we had before, assignment 24, is a really good one to go over as well. But we're going to go over some stuff right now having to do with the different simple machines. You guys remember all these different simple machines that we had? Well, I think, hey Reese, how's it going? So yeah, we got all these simple machines here, and you can see that simple machines, they come in all different shapes and sizes, but they all do basically the same type of thing, right? They reduce the amount of work that we have to do, or you could say to reduce the force. So whenever you put some sort of force into a machine, that's called the input force, right? So whether you're pushing on a lever or pulling on a pulley, that sort of thing, that's called the input force. And the force you get out of it is the output force. So the good thing about a simple machine is that you get more output force from the amount of input force that you put into it, right? So let's just go on to the next page. All right, so here's an example of how that works. This is a lever, and I don't know if you guys remember, the fulcrum is the part that's in the middle, right? You can also call it the pivot. The part you're lifting up is the load. And does anyone remember what the other side is called, where you press down on it? Do you remember what you call that part of the lever? Okay. There's a special name like the load. This one is called the effort. Okay, so that's what you put into it. But you can see you're putting 10 newtons of force into it. That's the input force. And you're getting 50 newtons out. So it's a really good deal, right? And so you guys might have tried this sometimes. You're trying to lift a rock or something like that. You put something underneath it and you put a stick. So you put another rock, you put your stick on top of the rock, and that acts as a lever, and you're able to lift up a big rock that you can never lift yourself, right? So maybe if you guys can just help me with these blanks here. First one, number one says the point around which a lever can rotate is called the what? What do you think that would be? Okay, so if you just imagine pushing this up and down, that's kind of like rotating, right? Where's the point where it rotates? What do you guys think? If you look on the diagram, what do you think it's called? It's the fulcrum, right? You got it. Okay, so there you go. So question number 2 says another word for the amount of weight lifted by a simple machine is the what? What do you call that? When you look at the diagram, it's the load. Good stuff. Okay, and we know the other side is the lever. So you can see here again that there's 10 newtons of input force and you get an output force of 50 newtons. All right. So now there's a really important word we talk about when we talk about this stuff with levers, and we compare the input force and output force. And I think that I might have put this on the test. I'm not sure. But if not, I will put it on the test. And it's called the mechanical advantage. And so basically you divide the output force by the input force. And so again, the output force is going to be larger, so you're going to get some number. So let's say you divided the numbers up above. You would divide 50 by 10, and so you'd get a mechanical advantage of 5. So that kind of gives you a bit of an idea of how good of a lever it is, right? Or whatever the simple machine is. Okay? So we need to know this formula here. Mechanical advantage is output force divided by input force. Good stuff. Okay, let's go on to the next page. So this is important to know. You could say that the force is being multiplied by a simple machine, right? Because you started with 10 and you multiply it by 5 and you get 50. Okay, so you can call simple machines force multipliers. Okay? So can you guys remember what the formula is for mechanical advantage that we just looked at on the last page? Something divided by something. Do you remember what goes on the top? Okay, 50 and 10. So what was the 50? Was that the input force or the output force? Okay, so the 50 was the output, and we divide that by the input. Good stuff. Okay, let's go on to the next question. The next one says, if a pulley is used to pull some tools into a barn loft and it takes 5 newtons of force to pull the rope, and the force pulling down on the tools is 45 newtons, what is the mechanical advantage of the pulley? Okay, so remember, output force divided by input, how much would it be? Can anyone tell me which of those numbers is our output force? Is it going to be the 5 or the 45? Okay, the output's going to be 45, right? Because you're getting more out of it than you put in, and the 5 is going to be the input. So what do you get when you divide 45 by 5? Okay, good stuff. So the next question, why is it that we talk about the multiplication of forces with simple machines? Why do we talk about that, multiplication of forces? Okay, would you agree that that's basically because of what we saw here? We multiply the input force by a certain number, which is the mechanical advantage, and that gives us our output force. Input times mechanical advantage is our output. Okay? So we already know that there's a whole bunch of advantages that come with simple machines, right? But we also know there's a few disadvantages. So let's look at those as well. All right, well, here's one right here. This person's trying to pull up 200 kilograms. That's pretty heavy, right? Normally you might not be able to do that. The thing is, when you're pulling on that pulley, you've got to pull all this rope. So you're actually pulling more distance on this rope than you would be if you were pulling it straight up. Okay, maybe just a few of these little guys here, okay? So there's going to be more distance you're going to be pulling overall. But the other thing to remember is it's going to take longer. So no matter what the machine is, it's going to take longer than it would if you lifted it straight up. So even though you're reducing the amount of force, there's always going to be a disadvantage with time and with distance. Okay, so remember, those are the two disadvantages of any simple machine. Okay, so if we look at this question here, it says, what's the advantage of any simple machine? What would you say? If you were trying to tell someone in your own words, you know, I'm going to use this lever right now to lift this big rock, what would you say? What's the reason why you're using it? What does it reduce or make smaller? Oh, sorry about that, guys. I'll just move it in a second. Be right back. One of these days I'm going to remember to move the phone. But sorry about that. It's going to reduce the force, right? Any simple machine is going to make the amount of force that you need to lift something, and it's going to be smaller. Now, do you guys remember what the two drawbacks are to any simple machine? What did we talk about when we just talked about that pulley? Who can tell me what one of them is? Reduces the force, but what's longer? Anybody remember? Okay, I'll give you a hint. One of them is time. It's going to be longer to use your simple machine than if you didn't use it. Can you remember what the other thing is? Time and what else? Good, distance. Right on. We both got it. Okay, good stuff. So we're going to look at another simple machine. It's a screw, right? Yeah, you bet. We'll give you a smiley for that for sure. There we go. All right. So when you're using a screw to put something in, right, what it does is it changes rotate. I didn't mean that. I mean my little hand. There we go. How do we get that back to normal? There we go. Okay, so a screw changes rotational motion. In other words, you're moving around in a circle, right? It changes it into straight line motion. So even though you're turning it around and round, the actual screw is going up and down, right? So that's what a screw is doing. And I don't know if you guys remember doing this. You might have read it in the lesson. I'm not sure if you actually tried it. But if you take something like this, a piece of paper that's kind of like a ramp, right, and you wrap it around a pencil, which is a cylinder, then that's going to make a screw. And so that just shows what a screw really is it's really like a ramp which is wrapped around a cylinder. Okay? So you can try that on your own if you haven't tried it before. Okay.
You have new mail.
So, just a sec here. Getting lots of new mail. Okay, so what type of simple machine did we say a screw has in it? When we're talking about that little experiment, what type of simple machine was involved in a screw? A ramp, that's right. Or you could call it an inclined plane if you wanted to. Same thing. Okay, so let's look at a wheel and axle. Those are kind of cool, right? And an example of a wheel and axle would be a doorknob. And so why do we bother having a doorknob? Like, why not just have this little thing here? Well, the reason is because when you have the big wheel, if you think about this as a wheel and this is a small wheel, it takes only a little bit of force on the big wheel to put more, you can put more force on this here, or you can do more turning, you could say, when you use this big wheel. It's like having a steering wheel as well, right? Okay, so let's look at a few questions. So first of all, what's the job of a screw? What type of motion is changed into another type of motion when you have a screw? Okay, it changes rotational motion into what kind? Good stuff. Okay, so how about if you're learning to drive, right? So you're there at your steering wheel, and you're moving the steering wheel. So I wrote here, what's the advantage of a steering wheel in terms of the forces involved with the two wheels? Or another way of saying that is, why do we have a big wheel attached to a small wheel? How does that help us? That's right. It's a lot easier to turn, less force. Good stuff. Okay, at this point we're going to look at something called linkages. And basically any linkage is a system where you transfer energy from one place to another. So if you're looking at something like a gear or a belt or a chain, those are all linkages. And so we're going to look at one of those right now, look at a couple, but first we're going to look at a bike chain. Okay, so we just imagine this is part of a bike chain. And so what's happening, you're pushing on the pedal over here, right? But because the pedal's part of a wheel, and that wheel's attached to a chain, you're taking the force that you're pushing here, and you're transferring it over here. Because that's what any linkage does, right? It transfers energy or force from one place to another. Okay, so you're transferring the force from the pedal eventually to the wheels of the bike, which is where you need it, right? So you can move the bike. So that's what it's doing. And so a gear is another example of a linkage. And when you have two gears together, the one that's doing the moving is called the driving gear, and the one that's moved is called the driven gear. Now the good thing about gears, they can change direction, but they can also change speed, right? And that's why you've got gears in your car, and they help you to go slower or faster. You know, you're listening to your car sometimes and you can hear it changing gears as you're going, right? Or especially with a motorcycle, you can even tell that more, right? And so yeah, you can change direction and you can change speed. So the question I have for you guys, if you want to make a driven gear that turns in the same direction as the driving gear, will you use 2 gears or will you use 3? What do you think? Okay, well check this out, guys. This gear is going to turn this way, and we call that clockwise, right? But as this one goes down this way, it's going to move this guy this way. And is that clockwise or counterclockwise? That's going to be the opposite direction if you have 2, right? So you're going to need 3. So does that make sense to everybody now? Why you need 3? Okay, good stuff. So, on to the next page. Rescued Luigi on Mario. Okay, can you tell us the story behind that, Natalie? No, I'm just wondering about Natalie's name here. Rescued Luigi on Mario 64. She's got my curiosity going. You know, as teachers, we're always curious. Okay. Yeah, I knew that. So I'm assuming you rescued Luigi, did you? Or did you just like the name, maybe? Cool. Is it hard to rescue Luigi? Ah, okay. I haven't played that game very much. I just bought our boys a Wii game for Christmas, and I got my son, my youngest son, he just turned 7, so I got him NHL 2K10, which is pretty cool. Yeah, I'm going to have to try that sometime. Well, now I know the history. I know the story. Okay, so we talked about simple machines, right? And most of the machines in the world that we see, they're not simple machines, right? They're complex machines. Now, this is a pretty bizarre machine, right? I don't know if you guys have ever seen a machine like this before, but, you know, I don't even know what this thing's trying to do. I guess whatever's at the end it's trying to do, but I can't even tell what it is. I guess, first of all, the toaster goes and then produces some heat, which causes a whole bunch of stuff to happen. Anyways, it's a very complicated machine, right? Now, the problem with complex machines, when we're talking about a complex machine, that it's usually made up of many machines together. So most things we have, like a car, they have a bunch of simple machines put together, right? The problem with complex machines is whenever you have parts move against each other, it produces what? You guys remember what it produces? I should hide this here. Yeah, it produces friction, right? So you rub your hands together, it makes friction. And so the more parts you have, the more friction you have. And so that's a bit of a problem, right? Because especially with a car, you know, the parts heat up and you need to have oil to take away that heat and stuff like that. Okay, we're just going to review a few things we went over recently. So first of all, guys, what's the purpose of a linkage again? Do you remember? It transfers something from one place to another. What is that? Think about the bike, think about the pedal. Okay, yeah, you could say it transfers energy from one place to another. Or you could say force, right? Force is just a push or a pull, right? So you could say the same thing. Okay, so what's a problem that results from all the moving parts of a complex machine? What do we say a problem is? Okay, Natalie? I see the happy face. It's complicated, but it's got all that friction, right? You don't want all that friction, all that heat. That's energy that's lost. Whenever you've got friction, that's lost energy. You don't want that, right? Okay. Now, I don't know if you guys remember we talked about work, And in science, work is kind of different than the work you do at home. You know, you can do work at home, and okay, well, I'll show you what the difference is. In science, work is always force times distance. So the thing about that, I'll show you a picture here. Okay, here's a big football player, right? I don't know if you guys have ever seen these things that big football players move or try to move. Well, in science, if a big football player is pushing that thing and it doesn't go anywhere, wait, can you see this thing here? Ariel? If a football player is trying to move something like this, but it doesn't move, in science we say the football player hasn't done any work, right? Because work is always force times distance. So the football player has force, but he hasn't moved the thing a distance, okay? So really nothing's happened as far as work in science. Okay, so it sounds kind of discouraging to do all out, you know, energy, but you haven't actually done anything. But, okay, here's another thing. In science, work done is equal to the energy used. Okay, so however much energy this person put into this is how much work that person can do. So work and energy are always equal. Okay, whatever you put into it with energy, you get out with work. And both energy and work are measured in joules. Okay, I can't remember where that name came from. There's probably somebody named Joule. That's where most scientific things come from. So anyways, so what's the formula, guys, for work? What would you say? Force times distance. Okay, so remember it should be times, right? Okay, so B says, what force is needed to lift a heavy box 2 meters high if it takes 1,200 joules of work to do this? Okay, no problems. So we got to figure this out because this one's a little bit trickier. Because this one's asking us for force. It's not asking us for work. So what we have to do here, we have to say work equals force times distance, right? And then we plug in the numbers we have. So it tells us we have 1,200 joules of work, and then it tells us that we're going to lift it 2 meters high, but we don't know what force is yet, and we have 2 meters, right? So this is what we have so far. 1,200 equals F times 2. So we can just call that 2F, right? 1,200 equals 2F. Okay, now I don't know if you guys remember this from the lesson, or I'm not sure if everybody's done this before in math or is familiar with this, but when you're solving an equation like this, and you've got 1,200 equals 2F, well, first of all, you can just think about it in your mind, right? You can think, okay, I'm multiplying 2 times some number to get 1,200, and that number is going to be 600, like Judy's saying, right? Now, if you wanted to do it in using math steps as well, it's okay if you did it in your head, but if you wanted to get the F by itself, you say, okay, that's 2 times F. What's the opposite of times in math? What's the opposite of times, guys? Divided by, right? Okay, so since we're timesing by 2, we're going to divide both sides by 2 to get rid of that 2. And when we do that, we're going to end up with just F on the right side, right? Because these 2's cancel out. If you have the same thing on top and bottom, it cancels out. Then we have 1,200 divided by 2, and that's going to give us 600. Okay? So you could do it in your head when you just say, okay, some number times 2 equals 1,200. Okay, that's got to be 600. Or you could do it using this. All right? So the last question, guys, on this page is, how are work and energy related? How would you say they're related to one another? Okay, you need energy to do good, to do work. That's good. Right on. Anything else? Work drains energy. Good. Need energy to do work. And would you agree also that the work done depends on the energy that you use is equal to the work done. So the energy you put into it is the work you get out of it, right? Okay, so on to the next page. So this time we're going to talk at this point about hydraulic systems. So for instance, if you go into a mechanics station, I don't know if you guys have been to an auto mechanic place before and seen work done on a car, but if you do that, you might see the car put up on a hoist, right? And so here's a hoist, lifts the car up. Well, I mean, you're using only a tiny amount of force here, right? You put a tiny amount of force in and you get a ton of force out. So we put a small input force into it, we get a large output force out of it. Okay, so it's just like another machine, right? You're multiplying the force. Okay, so force is changing with one of these hydraulic systems, but here's something that doesn't change. What doesn't change is the amount of pressure. The amount of pressure is the same. So you know you've got this liquid here, right? Some sort of liquids in here. It's an oil. The amount of pressure that's in this liquid is the same throughout the whole liquid. And that's true of any liquid that's in a container. If you press on it one place, it's going to put pressure the same throughout the whole liquid. Okay? So remember, pressure is equal to force over area. What I always like to do to remember it, I think about like high heel shoes. Okay? So if someone presses on my feet with high heel shoes, I'm going to say ouch, right? And depending on how hard they press, you know, but because they're putting force over a very small amount of area. But if someone put that same force on my feet, but they put sandals on my feet, they stepped on me with sandals, I'm probably not going to say a whole lot unless they really stomp hard, right? Because you might be putting the same amount of force, but you're spreading it over a larger area. So that's a way that can kind of help you remember what pressure is, that it's force divided by a certain area, spread out over a certain area. Okay? So I said before that the pressure is going to be constant in this whole liquid. And there's a law, it's called Pascal's law, and so that's what Pascal's law says, that whenever you have pressure in a liquid, it presses on the outside of the container with the same amount all over. So for instance, if you've got a bunch of air inside a balloon, it's going to press on all the balloon the same amount. Okay? So that's Pascal's law. So question 12 says, what happens to the force you put into a hydraulic system? Okay, you're going to put a certain amount of force in. Are you going to get the same amount out? You're going to get less out, more out? What do you think? You're going to get a whole lot more out, right? Yeah. Okay, next question. Using the pressure formula, calculate the force on the output piston if the pressure is 300 pascals and the area of the output system is 300 meters squared. Okay, so we've got to calculate the force. So let's do the math here. So, all right, we know pressure equals force over area, right? And so this tells us that we have 300 for pressure, and that's going to equal force. Doesn't tell us what the force is. Force divided by 3. Okay, I'm not even going to use the units here. Okay, so we're wanting to find out what the force was. And so in this situation, I'll show you how we're going to do the math here. Just a sec here. So 300 equals force over 3. Okay, so whenever we solve an equation, we always want to get just the variable on one side of the equation. The variable is going to be force, and just a number on the other side, right? The problem is we have this number here that's with the force. We want to get rid of that divided by 3. And what's the opposite of divided by 3 in math? It's going to be times 3. Good. Okay, so we're going to times both sides of the equation by 3. Okay, so we say times 3. And whatever we do to one side of the equation, we always have to do to the other side. Okay? So when we multiply both sides by 3, remember you have the same number on top and bottom, they just cancel out. We can just cross them out. Okay, so we're left with force on the right side of the equation, and on the left side we're left with 3 times 300, which is going to be 900. So the force is going to be 900. Okay? So that's how we would do that. And the next question, C part, says, what is the same throughout the fluid of a hydraulic system? Do you remember what's the same throughout the whole thing? Whenever you've got a liquid, what's the same in the whole liquid, throughout the whole liquid? Pressure. You guys got it. Good stuff. Okay, and Pascal's law. Okay, Pascal's law, remember that just means that pressure is always constant in a liquid. Okay, so that's all C is telling us, Pascal's law. Okay, so here's a question for you guys. Which of the following situations would not be considered work? Okay, so first one says, a boy pushes on a fridge with a force of 30 newtons. Does that work? B says a boy pushes on a fridge with a force of 30 newtons and it moves 3 centimeters. Does that work? C says a boy lifts a book. Okay, so somebody's given the answer. Natalie says it's B. That's right. Because in order to have work, we've got to have a force and a distance. All right? So that's why that one's going to be B. Good stuff. Okay, so the last thing we're going to look at this point is, remember we talked about pop cans and how they changed over the years? And I'm not even sure when these things were, because I don't even know when I was a kid, and I'm getting pretty old. I'm going to be like 44 in a week, right? But, yeah, it was a week from yesterday. So anyways, but I can't remember these things here, but supposedly at one point they used to have pop cans where the only way you could get into them was to use one of these things, okay? And this thing's called a church key, but you guys have probably seen one of those things, similar to that, right? Like if you were trying to open a can of juice, you've probably seen one of those. Okay, so that's called a church key. So they used to have those. Yeah, it's kind of different, eh? So they start off with step 1. So I wrote down here, step 1 shows originally pop cans would be opened with a church key, which meant you needed to have one handy when you want to open your pop can. The church key was an example of a lever. Okay, so this thing's actually like a little lever, this thing. Okay, you might have seen something that looks similar but a bit different. So what do you guys think is the main advantage from going from step 1 to step 2? What would you call that? Having something like this is called a removable tab top. And so what's the advantage, you think, of having something like that to having something like this? How would you describe it? Can you think of a word that would describe the ability to have something like this as opposed to not having it? Okay, how about convenience? That would be considered convenient, right? It's really convenient if you've got this thing built right into it instead of having to carry it, right? Okay, let's look at the next step. So next, step 2 says, it shows pop cans had the ability to open the can built right into it. It's called a pull top. However, the problem was these removable pull tabs came off too easily. Well, what do you think the problem would be with them coming off too easily? What if you were like a bird or something like that? You think you'd be happy with those? No, because those things might slice your throat, eh? You're like, I can't breathe, right? So these things were not good for the environment, not good for a lot of different animals, right? Okay, so that's why we went to step 3. And that's the kind we have right now. These are called non-removable tab tops. Okay, so these are removable and these are non-removable. So what do you think were the main 2 changes that we saw from going from step 1, 2 to 3? What 2 words would we use to describe the main 2 benefits from the original pop cans to the ones we have now? Can you think of 2 words? Okay, better in what way? That's true. You can break off the non-removable ones too, if you really want to mess with the system. Okay, so easier. Yeah, you could say easier, or we could say convenience, right? Convenient, good. Okay, and what's another benefit that we saw in the last step? Convenience was going from 1 to 2, and what would we call this going from 2 to 3? Environmentally friendly. Perfect. Good stuff. That's a word a lot of people are using these days, eh? Friendly for the environment. Good stuff. All right. Perfect. Perfect words. Okay, so basically by trial and error, the design of pop cans was changed over the years, right? The way they were designed, that's what we saw changing. Okay, and it was using trial and error. You try something, you see if it works. You know, you might make an error, but then you try something new. You learn from it, right? Okay. So I put here, what 2 advantages are there in the current designs we have? Okay, we answered that. Convenience and environmentally friendly. And next one, what was the main problem with the removable? Okay, bad for the environment. C, what was changed over the years? The design was changed, right? And you guys remember which design had a lever in it? Step 1, that's right. That was the church key. It was a type of lever. Okay, so I think we're actually done. Good stuff. You guys did really great on this. Appreciate everything, all your hard work on this. And it was cool to find out about Natalie's nickname. Actually, that's probably not your nickname, but you should make a shirt that has Rescue Luigi on Mario 64. That would be kind of cool. So, all right, I'm just going to stop the recording at this point. And just want to remind guys to write the test as soon as possible. And also to look over that assignment number 24 again before doing the test.